solar energy. My project mates were David, Emily, and Ray. Some information from Chapter 16. Solar energy technologies produce electricity from the energy of the sun, with smaller systems providing energy for homes, businesses, and remote power needs. Larger solar energy systems can produce more electricity and feed the electric power system, which consists of sun tracking capabilities, solar to electrical energy converters, and lines that supply energy to the grid or the AC loads. A diagram is given on the next slide. Here's an example of a solar energy system. Observe the panel on the left. It's collecting solar radiation, and through a system of power electronics, some of which we've covered in class, such as DC to DC converters or DC to AC inverters, it is converting the energy with the ultimate destination to the electrical grid. Solar energy, of course, is provided by the sun rays, which have a high energy density in space, as much as 1.353 kilowatts per meter squared. Now that power is lowered due to the absorption of some energy by various gases and water vapor in the Earth's atmosphere and the projection angle of the sun rays. In the next slide, we're going to derive the power formula. The solar power density on Earth, known as solar irradiance, can be determined by the following mathematical model, originally developed by Atwater and Ball. It states that the power of the solar irradiance is equal to the power of the extraterrestrial power density multiplied by the cosine of the angle between the sun's rays and the normal to the surface, which is theta. There's alpha dt, which is the daylight transmission factor, minus beta WA, that's the water vapor absorption factor, multiplied by alpha of P, which is the particulate transmission factor. In the next slide, we'll go through an example to show you how the solar energy is harnessed. Here's an example of calculating solar irradiance and the power that it generates. We're given some values. After the calculations, plugging them into the formula, we get about 0.7382 kilowatts per meter squared. This defines the amount of usable solar energy available per every square meter of the solar panel. Part of this project included an industry tour to look at some real-life applications. To observe how solar energy can greatly contribute, an interview was held with a senior electrical engineer at Lockheed Martin. Discussion was held about the implementation and contributions of a giant solar panel array that is stationed above their employee parking lot. Some of the questions included: when were the solar panels installed and why? How long did it take to complete the project? What is the energy used on? What's the impact of having the panels? And if there were any other renewable energy initiatives in action. Observe inside the dotted red circle. Those are the solar panels that they have installed above the employee parking lot. They're quite massive, and they generate a large amount of solar energy every day. This is the interview with the senior electrical engineer at Lockheed Martin, where he mentions that the solar panels were installed in mid-2018 with the original goal to help reduce the carbon footprint. It took about 6 months to finish installation and complete activation of the panels. One thing I thought was really interesting was just the amount of sheer energy that they do produce. At a given time during the day, the panels are producing about 1.7 megawatts. In 2024, the total energy produced was 3,000 megawatt hours. Just to put that in perspective, the average amount of energy to power a home is about 10,500 kilowatt hours per year. So just in 2024, they generated enough energy to power about 286 homes. The energy is used by the Lockheed Martin site, which helps to alleviate the pressure on the main energy grid and reduce his monthly cost, which after some time calculating came out to about $28,000 per month in savings, about $336,000 per year. I asked about any other renewable energy initiatives in action. He mentioned that the site currently has an ongoing project that will convert all the light poles to solar powered, which is an effort to further save on power costs. Lockheed Martin, and likely many other individuals or businesses that use solar energy panels, they leverage what is known as net metering, which is a billing system that allows solar panel owners to receive credit for the excess energy they generate, and it sends back to the grid. When their system produces more power than they use, the surplus is exported and they receive credits on their electric bill. Later, when their system isn't generating enough, like at night, they can draw electricity from the grid and use those credits. This helps lower electricity bills and makes solar energy more cost effective.
Hi, I'm going to go over photovoltaic cells, how they operate, and what they're made out of. So the word photovoltaic directly translates to light electricity. These cells, I'm going to refer them to as PV cells, are made out of semiconductor devices such as silicon. So the way they operate is that when sunlight makes contact with the lens focuses the light energy directly towards the N-type material. This excites the electrons and the N-type materials. These cells do have a special built-in electric field that provides a force needed to drive the current through an external load. So the electron gets excited and then moves towards the P-type. And this is how we are able to harness the electricity. PV cells are the building blocks of all PV systems. And for the next slide, I'm going to go over different types of PV cells. I'm going to go over different types of PV cells. So the first one I'm going to go over is the monocrystalline silicon. This is the most efficient but also expensive of the four. So the way this is manufactured is that a single crystalline silicon is dipped in a molten silicon. So this leaves very little impurities in the crystalline structure, but it leaves a lot of waste. That's why it leads to being most expensive. And once this single crystalline silicon is finished, it gets sliced up into what's known as wafers, little squares, as you see on the top right. For the second one, the polycrystalline silicon, this process is very similar, but it's no longer a single silicon that gets dipped, but a bunch of fragments. This does two things. The crystalline structure is not one, so there's a lot of impurities, which leads to inefficient. This method is a little bit more affordable, and that will be the trade-off. Thin film, a little less used, but basically a thin film solar cells are made by printing a coating of extremely thin layer of PV material on some sort of surface. This one's a little bit more flexible since you can put it anywhere, like windows or so, but this is rarely used, and other emerging technologies are perovskites and organic cells, which are still underdeveloped. Okay, PV systems, what are they? Well, essentially they're just PV cells placed in series and parallel to make a larger grid. So a PV cell alone doesn't create too much power, roughly about 1 or 2 watts only. So that's roughly a low power calculator. So when a PV cell is placed in series, this is called a module. This you can see at B, module M being the numbers of cells. And then when these modules are placed in series or parallel, they create a larger unit called array. And the equation below is just basically your simple power equation times the area, which represents the numbers of cells. So V times I is power, M and N are the dimensions of the cells. So it's surface area times the power equation that we're very familiar with. I'm going to go over the different types of inverter and the installation of these solar panels at homes. For the first one, the string inverter, multiple solar panels are connected in series, hence the word string, and there is one central unit that inverts DC electricity into AC. Some pros for this one is that they're cost efficient, easy to install, but some of the cons is that if one of the solar panels are underperforming, it affects the whole string. So this is one of the downsides. For the next one, micro inverter does fix all the problems for the previous one. In this one, each panel has its own inverter, converting DC to AC at each panel level. So this one, some pros is that each panel are closely monitored. So when it comes to troubleshooting, this process is a little quicker. Some of the cons is that it's definitely more cost effective because there are more components to maintain. Power optimizer is a hybrid of the two above, the string and micro inverter. Each panel has a power optimizer to adjust the voltage before sending DC to a central inverter. This is higher efficiency. The monitoring is just as effective, but some of the cons is that it still requires a central inverter where most of the problem could happen or incidents. Hybrid inverter will be the next one. This acts like a solar panel and battery storage device, converting DC to AC while managing battery storage for later use. This has become more popular with houses with electric cars like Tesla. Definitely more expensive, but some of the pros is that it stores electricity so it can be used later. Off-grid systems are the least common. Converts DC to AC by operating independently from the grid. So these are built on like farms and houses that have their own electric device, external electric device, because they're off-grid.
So the history of solar panels actually starts way back in 1839 when Edmund Becquerel discovered the photovoltaic effect. Then in the 1880s, Charles Fritz made the first solar cell using selenium, which wasn't super efficient, but it was a start. Fast forward to 1954, and that's when Bell Labs came out with the first silicone-based solar cell. A few years later, in 1958, NASA used solar panels to power the Vanguard 1 satellite, which was a big deal for space tech. And from the 2000s to now, solar has gotten way more affordable and is showing up everywhere on rooftops, farms, buildings, etc. Solar power is used in a ton of different ways. On the residential side, we've got rooftop panels that power homes. Then on a larger scale, there are solar farms that help run businesses or support agriculture. We also see it every day in everyday devices such as calculators and even streetlights. In space, solar is huge. It powers satellites, the International Space Station, and even rovers on Mars. And it's also important to more of a remote area like rural villages or offshore platforms where access to the grid isn't possible. Also, the military uses lightweight panels in the field to charge equipment, so solar panels also help with that. And finally, solar is great for standalone systems such as parking meters, traffic signs, and irrigation setups that need power but aren't connected to the grid.
Hello guys, my name is David and I'm going to be telling you about the role that power electronics plays in solar energy. Power electronics plays a huge role in solar energy, and some of the ways it does it is by the power conversion, the grid integration, the energy storage, and the maximum power point tracking. Alright, to start things off, solar panels typically generate DC current, and while that may be good, most of our appliances and most of the outlets we use in the grid typically operate off of alternating current. So to fix this, we use power. That's where power electronics comes in, and we use an inverter that is used to convert the DC output for the solar panel into AC. And another thing is the energy storage. The power electronics help to regulate the flow of electricity between the solar panels, batteries, and the grid, ensuring safe, efficient, and charge control. Another way that power electronics plays a role in the solar system is with the maximum power point tracking. The maximum power point tracking is an algorithm used in inverters and chargers and charge controllers to ensure that the solar panels operate at the maximum power output. And also another way is the grid integration. In grid-tied solar power systems, power electronics enable that the solar systems are safely able to be integrated into the utility grid, and they do this by synchronizing the solar output with the grid frequency and the voltage, allowing the solar energy to be fed into the power grid safely when available.
To wrap it up, solar energy is one of the most promising renewable sources we have today. We've seen how power electronics convert sunlight into usable energy for everything from homes to major industries. The insight from Lockheed Martin definitely showed us how it is applied in the real world. And overall, solar energy helps lower electricity costs, reduces carbon emissions, and it's low maintenance, making it a smart, sustainable solution for the future. And that concludes the end of our presentation.